Okay, thank you very much. This talk was originally submitted under session 4 about looking at new techniques and software solutions, looking at structural tools and workflows. Here we are in session 2, so looking at established techniques. So I'm looking a bit more retrospectively than I perhaps originally intended. But essentially, in context, we're looking at decreased volume of conventional discoveries, but increased complexity. And looking at unconventionals, we've got a big set of challenges to go with that. So more than ever, it's critical that we have a clear three-dimensional understanding of the subsurface when we're looking at defining traps. So whereas before we might have defined traps by simple reservoir maps, now we have lots of different kinds of computer models. What I'd like to demonstrate in this brief talk is that a key requirement for any credible trap appraisal is a robust structural framework model. So just to say in brief what I'm going to talk about, a quick, as I said, retrospective view of interpretation in the 20th century and how I would hope it's now moving in the 21st century, and then illustrate a couple of applications of how using a framework model can actually bring you a lot more forward information that you can get to enhance your trap description. So let's go back to the 20th century, and some of the more senior members of the audience may remember this style of seismic interpretation, 2D surveys. You have some sections and you pick some faults on the sections and you try to post them on maps and build up a picture of the fault pattern. And yeah, some of us still have to do this today in regional surveys. There's a lot of ambiguity in putting this together, but by using structural rules, we can actually push the interpretation in one way or another. So in building up a map from this kind of data, we might have questions about that fault map. Are these faults actually as we've drawn them? Have we joined them up too much? Is that one fault or two outlined in the blue there? Well, back in the 20th century, some of the interesting structural geological applications, and in particular from the fault analysis group at Liverpool University, encouraged us to look at the displacement variation on faults and understand how that related to some of the detailed work that they were doing in coal mines. And by looking at displacement patterns, you can work out that actually perhaps some of these structures that you're joining together because they line up are actually not just a single structure, but might be multiple structures with interesting interactions. So by applying some structural geological techniques, we can push the sparse information that we might have. Later on, 3D seismic surveys apparently gave us a route out of this. So then it became a vogue to just auto-track the horizons, and there is your final map. But if only it were that simple. Auto-tracking is a great reconnaissance technique. It does give you an instant picture of what looks like a fault pattern. But as soon as you start looking in detail at how the auto-tracking behaves at multiple horizons, you can see there's a great deal of inconsistency in the detail. And if you look at the fault patterns, you can't readily relate all the faults at different horizons to one another. So this is very challenging if you're doing anything specific with the faults, like restoration, understanding the kinematics and history, or trying to understand the fault seal. So a step forward, but it's not a final answer. So now I think the better way forward, and more of us are doing this, is to build a framework model in 3 dimensions. And what I mean by a framework model is an assemblage of surfaces, that is the horizons and the fault surfaces from the seismic interpretation, and these must all fit together correctly in the 3-dimensional space, that is the subsurface. So the critical elements in making that fit correct are the lines of intersection between the different kinds of surfaces. So we have fault-fault intersections, which in structural geology terms are branch lines, and we have fault-horizon intersections, which in structural geology terms are the separation polygons or cut-offs, which we often just simply refer to as fault polygons. Okay, so if we follow that method, we can bring together in 3 dimensions our interpretation of horizons and faults from both 2D and 3D seismic data, and then fit those together in a nice, clear, matching and internally consistent way. And still at this stage, we can't just take the data and automatically press a button and get it to work. We still have to use structurally informed methods to ensure that what we're doing is correct, so that the framework model is structurally robust as well as just filling the space. And those structural methods may include fault slicing the seismic, looking at the fault orientations, understanding the relationships of the fault lengths to the maximum displacements, because they follow interesting rules. We might also look at the along strike displacement variation to look at whether we have segmentation of the fault system, other faults coming in. We can look at the fault arrays, how do the displacements sum together across multiple faults. Or we might, on individual profiles, do some kind of section restoration to understand if in those settings, appropriate settings, those structures fit back together in geological time as well. So a lot of different structural techniques we can bring to bear to ensure that this 3-dimensional model, as well as fitting together in the space, fits together in a way that is structurally valid in terms of what we understand about how rocks deform in the real subsurface. So we've got now a pattern of faults and horizons, and because of that 3-dimensional consistency, I would suggest it's a much better description of a trap in a fault block than just an old-fashioned map would be. And to try and demonstrate that at its simplest level, here's a map of a 3-dimensional model. So it's a single horizon surface. Usual colours of red is the shallow, blues and purples are deep, and it's cut by a cross-cutting system of faults. And okay, how would we interpret that in terms of the age relationship of the faults? What is actually their geometrical relationship to one another? What is the connectivity of the fault block? And I think most people would probably look at this and say, well, that's a continuous straight line. So the north-south fault cross-cuts the east-west fault. And these fault blocks look like they're closer to touching. We might get more connectivity in that direction. So just looking in map view, that seems to be the way that it works. But if we just tilt it back a little bit, you can see that the exact opposite is true. The east-west fault surface is actually continuous and displaces the north-south fault into 2 halves. And if we look at the fault blocks, actually the connectivity, if there is any, is between the northwest corner and the southeast corner. So looking at maps, it gives you a very partial and incomplete and deceptive view of the 3-dimensional relationships. The faults form the side seals to these traps, to these compartments, so mapping the faults and building a framework model is essential to define the traps properly. Okay, I'd like to then move on to a couple of examples of how we can put this framework model into good effect. And the first example is trap analysis in terms of understanding the sealing relationships, following on from that previous cartoon. So we've now spent the last 20 years or more understanding how faults can operate as seals or otherwise. And we're now at a position where we can perform a multi-fault trap analysis in a variety of different reservoir types and automatically find the most likely leak points in a system in order to understand the degree of trap fill to illuminate our volumetric studies. And I can also throw in a mention here that we can do this at time steps going back into the past. So as well as the present day framework model, we can unravel its displacement on the fault network and do exactly what I'm about to show you at previous time steps. So let's look at a simple old-fashioned reservoir map of a trap. We've got an upthrown trap bounded by a set of faults. A couple of them are labelled. If we're thinking in terms of the reservoir structure, we've got some potential spill points out of the trap at the ends of the faults, shown by these stars here. We've got potential spill points off the map to the north and northwest. So we need to assess how do we fill this trap? Do we just fill down to the shallowest spill point? Well, that assumes that the faults totally seal, which may or may not be the case. So what we need to do is actually understand this in a three-dimensional context and build a framework model and understand what's going on at the faults, not just look at the top reservoir map. So taking a perspective view on that, we can first of all look at the arrangement of the key faults joined by a branch line, and the other lines drawn on there are the horizon cutoffs or three-dimensional fault polygons of the top and base reservoir that you saw mapped, and also a shallower reservoir as well. In the next diagram, we can look at we can use those lines on the first part to highlight where our target reservoir is sitting on the upthrown side of each of those faults. So we can focus in, having constructed our framework model, on the parts of the faults which are acting as potential side seals. And then we can further take that and look at where we might have reservoir units on the other side of the fault which are juxtaposing against our target reservoirs inside the faulted area. So the coloured lines here now represent where we have sand-on-sand juxtaposition across the fault network, and therefore these are potential leakage pathways out of the trap system. And the colouring on here is a computed property we call shale gouge ratio, which is one of our tools in assessing the sealing ability of a fault. So this is a key step in getting to the sealing capacity of each of these faults actually at the reservoir interval. So to go back into our three-dimensional context, we can compare that with the top reservoir structure, which is our top seal, and by assessing the top seals and side seals together, we can look at the place that's most likely to leak as we progressively fill the trap. And what we would find in this case is actually there's a weak point on this fault here, which when the trap is filling with buoyant hydrocarbons will leak before we actually reach any of the top seal spill points. So this is the critical point which is going to control the trap fill. So only by constructing a framework model can we get to a state of understanding how these across fault and structural spill points compete in a three-dimensional sense. Okay, the second example I just want to touch on is how we can use our framework model as direct structural input to helping us with tight faulted reservoirs where fractures are significant in contributing to the reservoir being an economic development. So if we've got a good structurally robust framework model, the fault displacements that are built into that model can be used as input to a boundary element model. And that allows us to understand the strain within the reservoir, and then from that we can directly understand the likelihood of fracturing and small-scale faulting throughout the area of interest. So basically that would allow us to take the fault network that we've constructed in the framework model and compute the strain tensor at all these points in the reservoir around the fault network. From the strain tensor, we can predict the likely fracturing, for example, these conjugate fracture pairs that might have occurred in the reservoir as a result of the faulting. And we can further use our subsurface model to look then at how those fractures would respond to an in situ present day stress, which is what will be critical in controlling their hydraulic conductivity. So this kind of approach can be particularly useful, for example, in tight reservoirs in the southern North Sea. Here's an example of Southeast Hotton, which is an inversion structure over this footwall shortcut. So that kind of movement produces uplift of the reservoir, gives us a reservoir strain map and a fracture pattern, and the fracturing corresponds in a gross sense with the permeability of received in the seen in the wells. Similar sort of thing in chalk reservoirs, a slightly more complicated input of the structural controls, but again, predicting the kind of fractures that we get in the subsurface, we can correlate that with the image log data that we get from wells and look for the correlation of image logged concentrated fractures with the areas of maximum strain in the reservoir, and also look at the correspondence between the type of fracture, conductive or resistive, in terms of its response to the in situ stress pattern. So essentially the in situ stress field is controlling the hydraulic behaviour of those fractures. So to conclude, the top reservoir map, although is a convenient shorthand description, it's not sufficient to really document a subsurface trap when it comes to choosing a trap for drilling. We need a proper 3D description of the rocks, faults, fractures and fluids that we have in the subsurface. So it's important going forward that we, as an industry, have for every geoscientist who needs them, the correct tools at their disposal and the ability to use them effectively. So this not only involves being able to use bits of software, but appreciating the underlying science behind the software so that those techniques are applied in a geologically meaningful manner. Thank you very much.
Thank you, Graham. Is there any one quick question from the floor? Mike.
Hi, Graham. I love these workflows, posting things like shell gap ratios, always nice process. If we're in a true frontier area, how reliable do you think it is? We've got to get some lift to sort of think about whether we've got sands or ones on our distributions. Do you think these are still possible, or is there a lot of uncertainty?
Though obviously the uncertainty is much greater in those sorts of environments, but you're constructing your gross depositional environments and you're hoping to find reservoirs and seals and source rocks. So to the extent that you can predict where they are, you can then at least have a first order experiment of playing with these parameters in all sorts of other ways, such as SGR. Often the first well you drill will be the one that gives you all the information you need for subsequent appraisal. So extreme frontiers, obviously it's more wildly uncertain, but it's still worth considering.